Right, so welcome everyone. Thanks for joining today on one of the APGC seminars. So we're talking on an issue today on particularly an area that's of key interest to the controlled environment ag sector, and that's all about certain aspects of energy use that can kill or cure a process energy, as we've seen certainly in the UK and Europe. Although Shamim maybe it's different, maybe easier in the States, but I guess not. Energy is still king. So Shamin's from UC Davis, a Centre of Excellence for Controlled Environment Ag. And today he's going to talk about net zero greenhouse production with geothermal and solar spectral tuning. Shamim, the floor is all yours.
Hey, good evening or afternoon, probably around UK. It's good morning for me. And thank you for inviting me for this seminar session. And today, I will talk only the net zero greenhouse production with geothermal spectral tuning. So I know I should say that towards net zero, but anyway, the net zero is fine, like in terms of the title. Before starting my talk, I will just will provide a quick overview about the controlled environment agriculture. Like when we think the controlled environment agriculture, it's mostly traditionally it comes to the greenhouse production, and I would like to kind of present an overview of the global greenhouse productions at current time. Like even if you consider around this time, 2023 or 2025, this number is probably around 40 plus right now, like in terms of the now. But if we see that what could be the possible expansion by 2028 around that time, it could be almost close to the double. And if you see that the CAGR growth rate is about 11%. So another form of the controlled environment ag is the indoor vertical farming, and indoor vertical farming, this is the current market, and we're expecting around 9.7% CAGR expansion rate, although the indoor vertical farming has lots of kind of challenges right now the industry is facing. But overall, we can see the controlled environment ag industry is being very popular throughout the world, and it's getting greater attention from the government and policy level to kind of see as an alternate form of the agricultural production. In general, the overall market, so right now we can think about around 120 or around US $1 billion equivalence market, and we're expecting by maybe it could be 172 by next 2 or 3 years. So that's again is kind of give an indication that how the controlled environment ag industry is kind of expanding throughout the world. And this map is showing the expansion rate of the indoor farming in general as a whole, the controlled environment ag in different part of the world. So you can see the North America and Europe, it's relatively higher expansion rate compared to the other part of the world. But as I said, the controlled environment ag is being very popular because of many reasons. One thing is you can grow year-round production, and at the same time also the water use is very efficiency is very high, and also you can tune the other resource uses so that you can minimize the impact on the climate. But in terms of the cost of the controlled environment act, it's the energy is one of the biggest challenges that put the greenhouse or the indoor farming industry in a challenging condition. So this is one of my research. We try to see that even in the cold region in greenhouse production, the heating, cooling cost and others energy related costs could be about 30% or around that number. That's almost close to the cost for the labor, or to some point higher than the cost for the labor. That's one of the biggest challenges is kind of greenhouse industry is facing. So you can reduce the labor cost with the automation, but in terms of the reducing the energy cost, it's very challenging, based on the current technology to reduce the energy cost. But there has some different engineering and others plant sense aspects, some practice or design level things to reduce the energy cost. And most of my presentation today, I will keep my focus on the greenhouse aspect. This is showing for the indoor vertical farming. So this is indoor vertical farming. Mostly the energy is required for the artificial lighting, and that's why it's mostly the electrical energy consumption. This is in also the greenhouse and indoor farming production in different part of the world. You can see what is the specific energy consumption. This is for the lettuce. Either it's a plant factory, means completely indoor vertical farming, closed greenhouses means high-tech greenhouse. And when you think about the open greenhouse, it's relatively low-tech greenhouse. So from that perspective, like you can see, like for 1 kg of the lettuce production in it's the energy consumption, especially even in the greenhouse, it's quite significantly different depending on the location. That means the technology, even the talk that I will present, just very location dependent. It's maybe one area it's going to be very perfect, but the other area it could be challenging, or the specific benefit will not be kind of at to that level. This graph is showing about the CO2 emission for per kg of lettuce production from controlled environment ag. So most of the time when you talk with any people who work in the controlled environment ag, our main focus is that it's a very efficient in terms of energy, water, but at the same time, we can see that it's a very energy intensive. That means the energy that you are using, it's causing the environmental impact or the greenhouse gas emission. So in that perspective, you can see like this is the conventional vertical farming or the plant factory, for the amount of the greenhouse gas emission per ton of the lettuce production. Whereas the conventional greenhouse is all very significantly low because of the low energy consumption. So to some point, you can see like the conventional greenhouse and open field greenhouse gas emission is almost same. But if you try to think that advanced greenhouse, that's going to be the most of the part for the talk today, it can significantly reduce the greenhouse gas emission. So let's provide a little bit background about my lab. So I'm the working in the control environment engineering lab. In this lab, most of our research focus on like we call the sustainability aspect. Like it's usually called the people, planet, profit. So most of our research and technology that we try to investigate, we try to see that how that things will ensure the three pillar of the sustainability. And I would like to also provide a little bit background about net zero if it's not familiar to you. So when you think about the net zero, it could be the net zero energy or it could be net zero carbon emission. So most of our research, we try to keep our focus that how you can ensure that you are close to the net zero or towards the net zero. So let's say I mentioned at the starting of the presentation that I should say that towards net zero, because the technology that I will present today, there is no guarantee that it will achieve the net zero, but it will help us to bring the gap between the current status and the net zero status. So when you talk about the net zero, it means like if you talk about the net zero electricity, it means like the amount of electricity that you are consuming, and if you can produce same amount of energy from any clean energy source or on-site production, then we can call it the net zero status. And net zero carbon, again, it's the same things. Like if you, let's say if you produce 1 kg of lettuce and if you have like 10 kilogram of the carbon dioxide emission for the different activities that you are doing, but if you have the technology that can help to do that carbon sequestration, let's say if you do the clean energy production that can kind of subtract the amount of the carbon dioxide you are generating from other activities. So as long as you are kind of making that balance, the amount of carbon dioxide emission that you are creating, at the same time, if you have some practice that can minimize same amount of the carbon dioxide emission, then we can call it a net zero in terms of the emission perspective. So there is a different path to achieve the net zero, especially like when we talk about any building system. The greenhouse is the building, right? So in that case, it could be the on-site. First thing is efficiency, like how you can improve the existing efficiency. That's one of the main focus for my lab. And then we try to focus, okay, what could be the possible option to improve the technological development so that like you can generate the power on site. And the last one is like the circular economy. We also try to work a little bit on that aspect, but that's not our main focus. We mostly keep our focus on the energy efficiency and on-site renewable energy generation. So today, my talk, mostly I will keep my focus like how you can improve the efficiency of the greenhouse system and of that a little bit on also like on-site renewable energy, that what could be the different scope of harvesting the renewable energy system to reduce the carbon footprint for energy intensive greenhouse production. As I mentioned, like in the whole talk today, you will see like mostly two major things. One is we call the spectral tuning for the greenhouse, and another is the geothermal. So the first I will talk about the different project that we are working on, the spectral tuning of the solar radiation. And in that case, like we will at least present 2 or 3 technologies and related to the spectral tuning technology. The first one, we will talk about the quantum dot. I think if you are familiar with the quantum dot, what they do, like they shift the spectrum of the solar radiation. So based on shifting the spectral of the solar radiation, we can do manipulation of the lights that's is coming from the solar radiation, so that like we can see that like we can provide the lights based on the plant requirement. So if you're from plant science background, I'm not though, but like we know like the photosynthesis, like the way the plant response is based on the Macri curve. That means plant is more inclined to the red light than the blue light, than the green light is the third in terms of the absorption efficiency. So that means like what we can see, especially the environment like in UK. So where you can see that like probably most of the time is cloudy. So in that case, like you will see very low intensity for the red light, and those red light is very important for the plant growth. So what the quantum dot do, it's basically, I'm working with one of the industry, they call the UV-Kit. So they use the quantum dot technology, and what they do, they shift the spectrum. Let's say like if you have the blue light 100%, like let's say 100, it could be any unit like watt per meter square or micromoles per meter square per second. Let's say if you have 100 blue and then let's say 150 red, but let's say some plant they need more red light. Let's say the plant need 200 micromoles per meter square per second for optimal growth. So in that case, you can shift some of the blue light to the red light, and you can provide the optimal light that's required for the red spectrum. So that's basically quantum dot do. So now you can see it's changing the spectrum. You can see here is more blue or the UV portion of the light, but after passing that quantum dot plastic or the film, it changed the spectrum. You can see the blue portion is less, more on the yellow or the red portion. That helps to kind of boost the crop growth, especially where the solar radiation or the cloudy, like the cloud is one of the issue in terms of getting the optimum sunlight. And this is showing the spectral tuning. You can see it's the photon flux density and the transmissivity. This is the sunlight. Like if you see this is, if you plot the sunlight for the different spectrum within the photosynthetically active radiation, it will look like this in terms of the intensity. Now, if you see, this is the control means like the traditional plastic, and this is basically the quantum dot plastic. So you can see like they can shift some of the blue light to increase the intensity for the red light. That's basically in terms of the photon flux density intensity. Now you can see the transmissivity. In this case, the quantum dot has a low transmissivity to the blue, like around 50%. But if you see here, like the traditional plastic has efficiency transmissivity at 90%, but it can increase the transmissivity almost 98 or close to the maximum level. So that's kind of the technology that helps to kind of transfer some of the UV or the blue light and shift that to the red light to increase the efficiency. So our talk today will not be based on the plastic, it's based on the glass. So we are working with the UV-Kit to design a quantum dot glass, and to see that like traditional horticultural glass commonly used in greenhouse production, how this technology helps to kind of improve the efficiency of the greenhouse in terms of the thermal environment as well as in terms of the crop growth. So in this case, like as I mentioned, we tested 2 different things: standard glass greenhouse and with the quantum dot laminated glass greenhouse. So this is kind of showing the picture of our experiment. You can see this is the quantum dot greenhouse from 2 different angles. This is showing the conventional horticultural glass greenhouse. Again, this is a very small prototype greenhouse. but this was the pilot testing. So I think that should be okay. And it could be very easily the outcomes from this greenhouse could be scalable, or we can expect the similar outcomes for the large scale production too. This is showing the spectrum for the quantum dot glass. Again, like the same things that I showed in the previous slide for the glass, that we can see the almost we can get the similar trend for the quantum dot glass too. So you can see like below the 380, it's like kind of transmissivity almost like the intensity is very low because most of the light is reflected. But you can see it has a kind of very high transmissivity for conventional glass, and then you can see like how the percentage change of photon flux density is changing. So you can see like more on around the yellow or the red range, like you can see more of the light that's quantum dot is shifting that light. So this is kind of showing the outdoor control greenhouse and the quantum dot greenhouse in terms of the PPFD or PFD intensity. So we can see this is the outdoor intensity, and you can see the compared to the control. This is basically ubiquity or the quantum dot glass. So you can see there is the intensity is low, then you can shift that things into the blue, the yellow or the red zone, and that's kind of doing that, shifting that blue basically to the red and increase the intensity on the red spectrum. That's basically help plant to increase their yield, especially in that case we did for lettuce. And we'll try to present the different performance metrics. As I mentioned, first we will try to present the thermal environment aspect, and then we'll talk about in terms of the quality and also the yield. This is basically showing the indoor thermal environment, because this is important. So when you're shifting the spectrum, that has always impact on the indoor thermal environment. So we would like to make sure, okay, compared to the conventional glass, that it's not going to be impacting indoor climate significantly. The first, the figure on the top, it's showing the for 1 month full growing period of the lettuce. So like the QD means the quantum dot, and this is means the control horticultural glass. So you can see it's kind of the temperature wise, it's kind of almost consistent, and you can see this both greenhouse was not control the temperature with anything except the ventilation. The ventilation opening was same for both greenhouse, and we can see like it's almost identical temperature we can maintain. But for the greenhouse or any control environment, it's not only about the temperature, it's called the BPD, vapor pressure deficit. That's the combination of the temperature and relative humidity. So we can see when it's still like in terms of the VPD between control and QD, it's like kind of very similar trend. And we can see like not very big change in terms of the indoor thermal environment inside the greenhouse. So now let's see, like we found that like no kind of very difference in terms of the thermal environment, either temperature or BPD, but the plant is more critical about the DLI. For sure, the temperature and the BPD is important, but you can control that things with any additional system, but you need to have like also the same outcomes or to some point better outcomes for the DLI, the daylight integral. That means how much light is coming inside the greenhouse for the whole day. We call the mole per meter square per day. And we can see come for different day throughout that growing period, we can see like it's kind of almost identical, but to some point, it's even one thing I would like to kind of keep that in mind. Like you can see it's not difference kind of very widely, but what you can see that in QD film or QD glass, in general, it has a very small kind of decrease of the total DLI compared to the control. That's for sure. It looks negative in one sense, because you need to some point have the higher DLI, especially the region in UK and some other season where the solar intensity is low. But we'll see that benefit even also, like even if you have a low DLI, but we'll see the different outcomes in terms of the yield and other aspect of the plant metrics. So the first, let's talk about the yield and the morphology and how this shifting is impacting the lettuce yield and the other morphological parameter. So you can see the leaf numbers, canopy diameters, leaf area, fresh biomass, dry weight. So all aspect you can see, even although we have the low DLI, but we have almost significant for most aspect, like that it has a significant impact in terms of the increase in the leaf number, canopy diameters, fresh weight, and dry weight. So that's indicate like why it's shifting, because like when the blue light intensity is high and the red light intensity is relatively low, so if you can shift some of the blue light to the red light, and that helps to kind of increase the yield or the other morphological parameters, especially for the lettuce in that case. And now if we talk about the dry matter contents and root length, the root length, again, so you see the significant difference is a very like kind of, we always get surprised like how the root is even different. And we found even why the root was different. The one reason was I did not show that results, but we found that even when you have the ubiquity, the air temp, the water temperature for the hydroponic system was slightly higher. I think that can probably, that was the reason to kind of boost the root length. So now let's see the mineral composition of these two different aspects. So we can see usually for ubiquity, like for NPK or the calcium, magnesium, and sulfur, the uptake was to some point significantly higher compared to the control because of better light spectrum inside the greenhouse, and also relatively high temperature for the nutrient solution. For other minerals like bronze, zinc, manganese, iron, or the copper, some cases like we see a little bit opposite trend, especially like if you see the zinc, in ubiquity it was high, but like if you go to the manganese, the control was high, and also the same thing for iron, the control was high. Sometimes it's very difficult to explain, and I'm not plant scientist, but my colleague who is from the plant science background, she provided some of the explanation for this difference in our manuscript. But I will skip to explain some things that maybe not my expertise. Now, when you see the quality metrics, like you can see, like in that case, like we found a little bit less chlorophyll content or chlorophyll index in the QD flames. I would like to take kind of one explanation in that case. Basically, when maybe, again, I'm not plant scientist, but I will try to explain based on my understanding from the reference. The chlorophyll contents could be A and B, but you can see like in that case the red light mostly like reflect or the kind of react with the chlorophyll B, probably, or green light, they react with the chlorophyll A and B. So that's why like when you have the more balanced light, it will give the high chlorophyll index compared to the QD flame. So in terms of the other quality metrics, like we really got the slightly reduced the total phenolic content, but we got the higher content of the glucose, but at the same time we got a little bit the reduction of the fructose or the sucrose, but those are not statistically significant in general. So we can say, in general, the overall the QD flames had helps to increase the yield and the other morphology and some mineral composition inside the plant. So that's kind of giving the outcomes. Okay, like if you have the low intensity of the solar radiation, or let's say if it's cloudy, so in that case the red light intensity is very low. So in that case, like if you can use the QUD flame that can shift some of the light from the UV or from the blue rays to the more important, the red lights, to enhance the boost and also to kind of increase the mineral content inside the plants of that growing in greenhouse. Now I will shift to another of our project. The previous one, we work with the industry to kind of design the quantum dot flame. But this case, like we call the cool cover, this is kind of very early stage of the research. So we still kind of doing that evaluation in terms of the theoretical modeling and the optimization. So we call the cool cover. So what is the cool cover means, like especially the regions like California where solar intensity could be very high, especially in the summer or even the spring or the fall around that time. So because of that reasons, the indoor heat is too much for greenhouse production. That means the cooling cost is very high, and the evapotranspiration is also very high. from that perspective, it could be very challenging for growing crops. The regions like where the solar intensity is very high. From that perspective, we try to see, okay, what can we do? Like if we can optimize the light that's coming from the sun and the transmissivity of that light inside the greenhouse based on the Macri curve, that means like more red light, then relatively less blue light and very low intensity for the green light, then and also reflect the infrared or the near infrared, because all the heats that's we can think about it, it's almost like 50% is light from the near infrared around that regions, and those light, if those light is coming inside the greenhouse, that's not going to be beneficial for the crops. It's basically the heat, and that means your cooling loss going to be too much high. So we try to kind of optimize the glass basically in that case, although we said cool cover, cover means is a glass, it's not a plastic. So we try to see that like how that things is kind of beneficial in terms of the greenhouse production. And this is kind of the slide I already a little bit covered. So the light coming from the sun is a shortwave radiation. And this, if the all shortwave radiation is coming inside the greenhouse, it will build up the heat. And if this heat cannot escape, it will increase the indoor temperature. And you can see this is kind of showing the energy use for different location in Spain. Like I think you can see in Almeria, like where is the cooling cost is quite significant, almost like close to the heating cost. And when you think about the greenhouse, most people think about the heating cost because they think the cooling cost is very low, but it could be quite significant, especially for the modern closed greenhouse. So I will give very brief about the technology or the optimization because those are kind of more engineering aspects. So what do we try to do? We use the different materials to kind of design the glass, and we optimize all of this material composition, their thickness, their optical characteristics, and so that like we can reflect most of the IR radiation and also tune the lights. That means like we'll ensure that the red light will be kind of the transmissivity almost close to the 100%. Then blue light transmissivity will be around 50 or the 50 plus, and we'll try to keep the transmissivity of the green light. So that's way we can optimize the crop production and also optimize the thermal management. So this graph is showing our optimized results. So you can see this is the coating plus glass. This is conventional glass and the coating. So you can see in terms of this is showing the reflectivity. So that means you can see that it has a kind of very high reflectivity in that regions. Now you can see like in terms of the transmissivity, you can see this is the traditional glass. Like if you see the traditional glass, it has almost high transmissivity throughout the spectrum from the far until to the near infrared radiation. But in our case, like we did the coating plus glass. So that means if you, let's imagine this is the practical case, the coating plus glass. That means we put the coating on top of the glass. So you can see it has quite good transmissivity in terms of the blue around that, like around 80%. Then we significantly reduce the transmissivity into the green. Those are not critical for the photosynthesis, but to some point the green light is important too. So we try to keep the transmissivity around 40%. Then we increase the red light transmissivity again to the 80%, and you can see within the near infrared the transmissivity is almost close to the zero. So that's basically the doing the benefit to enhance the performance in terms of the energy cost. Let's see the performance of this technology. We try to investigate in 3 different climate, like arid, semi-arid, and also the Mediterranean climate. So in this case, we consider a couple of locations. In arid, we consider Phoenix, Riyadh, and Aswan. And in semi-arid, we consider Mosul, Fresno in California, Monterrey in Mexico. When you talk about Mediterranean, we consider Almeria, Spain, Clermont in Italy, and Marseille in France. So we consider almost the common 3 reasons where the cooling cost is significant or the high solar radiation is a problem. So this is the case study results in semi-arid regions. So I'm just showing the result only for one location, especially for the crop water use, the pen pad water use, and the power consumption and the yield aspect. This is for the Fresno in semi-arid regions. So as I mentioned in the comparison, you can see it's a cool cover and the conventional glass. Cool cover means our design glass and the conventional horticultural glass. So you can see as it can shift the light kind of very significantly in terms of reflecting the IR radiation, and also to some point some shifting within the PAR. It can reduce the evapotranspiration significantly compared to the conventional glass. This is showing in terms of the fan pad, because in that case we use the fan pad system for cooling the greenhouse. That's commonly used for any greenhouse production in these regions. So as the cooling load, like as I mentioned, like if you can reflect the IR radiation, so that means you can significantly reduce the cooling load. So as long as you have low cooling load, the water used for the evaporating cooling system will be significantly high. This is showing in terms of the overall energy consumptions, like in terms of heating, cooling, and we can see it's in that case also the glass that we design or optimize, it can significantly reduce the power consumption for the whole greenhouse. So, and we can see in terms of the yield, as I said, like in that case, we found even the relatively higher yield in terms of the dry matter per square meters, because you can minimize the high evapotranspiration that could be a stress condition for the crops, and at the same time, you can maintain the temperature within a very optimal level with reduced near infrared radiation, and that helps to kind of boost to the crop production. Again, in that case, we also consider the lettuce. So this is showing the three regions in the semi-arid regions, in that case Fresno, Mosul in Iraq, Monterrey in Mexico. We can see in terms of the normalized value in terms of the crop water use, pad water use, and the power consumption. So you can see it can significantly reduce, like on an average, like more than 40% reduction in terms of the crop water use. It can reduce almost, it's a very different from 32 to 80% reduction in terms of the pad water use, and we can see the power consumption reduction could be 33 to 81% depending on the location. Especially the Fresno, it's more efficient in terms of the pad water use and the power consumption. But this efficiency could be a little bit low, especially for the pad water use and power consumption in Montreal. This is all about the climate, so I'm not going in depth after that. This is showing the similar outcomes for the arid region. So it's the performance is slightly low, but still it's kind of very significant, or like kind of, I would like to say it's a very high number of the savings in terms of the water use, in terms of crop transpiration and the pad water use, as well as the overall power consumption. And we can found almost a similar trend also in terms of the yield that we forecasted based on this particular climate. Again, this is showing the three different locations: Phoenix, Riyadh in then Saudi Arabia, and Aswan in Egypt. And it's, as I mentioned, it's relatively low in terms of the water savings, and also to some point, like for some regions this looks high, and some regions, like especially in the Phoenix, like the pad water use was less compared to the Fresno, California aspect when you talk about the other regions. Now, if I move to the Mediterranean climate, so in that case, you can see in that we just consider the Almeria, Spain. We can see also very significant difference, or kind of very large savings in terms of the water use from the evapotranspiration, and also the water use for the fan pad. And you can see the overall energy consumption was kind of very high. So you can, one thing I forget to mention, all analysis we consider from May to September, because that's the peak period where the water consumption is very high and the greenhouse is mostly relies on the cooling. And so that's all discussion all about around that time. So in that case, like we can see also similar trends in terms of the yield. Again, that's could be because of the reflecting the lights, and that's not critical for the plant, and also ensure the transmissivity very high of the red light and also the blue light. This is showing the comparative for three different locations: the Almeria, Palermo, and the Marseille. And you can see it's also kind of almost like close to 50% efficiency in terms of, or more than 50% for water use, per water use is basically, it could be even to some point like to 90% savings, the reasons like the Marcel. And fan power consumption or the overall power consumption for greenhouse, you can see it could be reduced significantly. This is because the cooling cost you can reduce a very large number by very large number, so that like the water is almost like kind of less than 10% compared to the conventional glass. At the same time, as the cooling cost is a very low, you can expect like the fan power consumption will be significantly lower in that particular case. So that's kind of showing the benefit of this cool cover technology, how these things helps to improve the water use efficiency, reduce the water consumption for the cooling dominated regions, and at the same time it can significantly reduce the energy. So that means you can see this is kind of give you the picture that how these things helps to minimize the impact. Like if you can reduce the water use, especially the regions like the California where water is the big issue, you can significantly reduce the impact or the carbon emission from this agricultural production. The energy reduction that can help also to achieve the net zero energy as well as net zero production in terms of the emission, because if you have the reduced energy, that will helps to minimize your dependency on the fossil fuel, and that way you can minimize the impact also in terms of the emission. Okay, so now I will shift to another aspect of my research we call the solar energy generation or the agrivoltaics. I will try to keep the discussion kind of very brief because of the time, but I will be happy to explain more details during the Q&A session. So in that case, we designed the semi-transparent PV technology for greenhouse integration. As I mentioned, the plant in terms of the photosynthesis is more response on the blue and the red. And so that means our main focus is like how we can ensure the light transmissivity based on the power like photosynthetic active radiation for the plant, and we'll try to harvest most of the energy from near infrared or UV, and that was our focus, like how we can optimize the plant production, power generation for the PV, and also ensure the temperature, because if you can harvest the energy from the near infrared or infrared, you can control the temperature or indoor thermal environment. So this could be our collaboration with the industry, like from Mirai Solar from Saudi Arabia. So we are designing the shade skin inside the greenhouse with the PV module we call the retractable PV skin, and how that things helps to kind of control the light inside the greenhouse and how its things will be beneficial. We also work on the tracking based system. So this is horizontal tracking based on just the outside solar radiation. But we also trying to investigate like more on the incline blind kind of similar system that you have for your windows, and we kind of make the dynamic control of that things inside the greenhouse as a replacement of the shade skin, and see that how that things gonna be beneficial. We also work on the Lawrence Berkeley National Lab to kind of design the solar cell mostly on the silicon-based solar cell, because silicon-based solar cell is more stable and high efficient in terms of the power conversion efficiency. So traditionally, any silicon-based solar cell is the non-transparent and opaque. So we'll try to keep our design for the silicon-based solar cell to ensure that how the silicon even could be a transparent or semi-transparent, to ensure that it will provide the lights that's required for the plant, and also maximize the power generation with high efficiency solar cell technology. Our initial case, we just tried to conventional shade skin, like more checkerboard design of the PV skin in horizontal and the incline deployment. So I will quickly go and we try to show you like how it's beneficial in terms of the conventional greenhouse, horizontal PV integration, and the incline PV integration. So we can see to some point is beneficial compared to the conventional in terms of the heating and cooling load, as well as it enhance the power generation. And we can see the power generation is higher with the incline because of better orientation of the solar cell to the solar radiation. So you can see this integration could reduce the 18 to 22% of the total thermal load in the summer and 3 to 7% in the winter time. And the power generation in incline modules is 35 to 40% higher in the summer and like 13 to 15% in the winter time. I will quickly go this slide. Also, it's showing the benefit in terms of the cooling load and the heating load, and we can see is the cooling benefit is quite significant, but the heating benefit is not very significant, but still to some point it's doing some benefit because of the low intensity of solar radiation in the winter. This is showing the water savings, as I mentioned, like if you can reduce the high solar radiation, that's not important for the plant, especially the near infrared spectrum, and that can helps to reduce the water savings. And you can see that compared to the conventional greenhouse, it's the water saving is quite significant. As I said, like it's 22 liters per meter square of the greenhouse, where it could be only 13 liters per meter square with the PV scheme. And also in terms of carbon emission, we can see significantly reduce the carbon emission. The conventional, it was the 7 kilogram per meter square in July compared to the 4.8 kilograms with the horizontal PV scheme. This is like the CO2 emission reduction. Then we try to also compare the performance of this technology in different location based on the ASHRAE climate. We consider the climate A, like very hot and humid, and then hot and humid, and also climate 2B, hot and dry, warm and dry. Like this way, we try to kind of compare the different climate zone, and we found almost kind of significant improvement in terms of the total the thermal load. That means you can significantly reduce the thermal load, and also you can boost the power generation. You can see like it's quite significant amount of power you can generate. Like you can see it can generate like almost like in that, let's say in the Las Vegas, it can generate 125 kilowatt of energy per meter square, whereas the total energy consumption for Las Vegas will be, let's say, like if we combine this all three, it's gonna be like almost like 30 to 40% of the total energy consumption. It could be covered from the PV scheme integration. So now, as I said, like we also work on the design the silicon-based solar cell to make it transparent. So in this research, we try to work with the Lawrence Berkeley National Lab to design the optical nano antennas for visibly transparent solar cell. So we optimize the nano antenna of the solar cell, and then we try to kind of shift the transmissivity. So you can look at in this diagram especially, so you can see below 400, like the transmissivity is quite low with this design optimization. Then we can see it has high transmissivity around the power regions and very low transmissivity around the 800. Those are more on not critical for the plant mostly. So this is kind of very early stage of the research, still kind of we're designing the solar cells. We haven't tested that technology in greenhouse. We are doing further optimization to ensure that how we can improve the efficiency of the light, especially near the 700 or 750 around that range, because some recent study they found that the light after the 700, like called 750 or 780, some people call extended PAR, is also critical for the plant. So we try to kind of see that what could be the possible way even to increase the transmissivity within this spectrum, like 700 around. And based on that, this is our very recent results. We can see that in terms of the transmissivity. So we try to keep the transmissivity around 60% within around blue, then significantly reduce for the green. And we can see we can increase the transmissivity even for the 700 or around that range is like 90%. But one problem we can see, even after 800 now, it's the transmissivity is high, which is mostly the heat. We are right now working to see that how even we can optimize to reduce the transmissivity just after 800, so that it's not increasing the thermal load inside the greenhouse. Okay, that's all about the solar spectral tuning. I know like probably I already covered 40 minutes for that, but I will quickly try to also present about the geothermal application for the control environment ag. So as I mentioned, like my lab mostly focus on the different approach for the renewable energy integration, and geothermal has a huge potential in terms of the greenhouse application. Again, these are all location dependent solution. So in that case, we try to focus on two different aspects, like conventional ground heat exchangers. That's also geothermal, but without any heat pump. So it's during the heating or cooling mode, how it's like kind of just changing the loop. In the heating mode, you're just pumping the cold water or air inside the ground, and then after heating up, you can bring it back. In the cooling is opposite, so you can basically dump the heat inside the ground, and then after cool it down, you can return that things, and then you can cool it down. So in that case, this is the ground heat exchanger, this is the heat pump. So we try to kind of investigate both technology as a solution compared to the evaporating cooling pad and the boiler based heating system. And we try to see that if we integrate this solution like the ground source heat pump or ground heat exchanger, how it will perform compared to the conventional evaporating cooling pad or the boiler based heating system. This study all about California, we try to see that, okay, I skip the other technical performance, but this is gonna be give you the very close enough good information about the benefit of this technology. So you can see the water use, carbon emission, and the operational cost for two different seasons. For one location is the without CO2 enrichment. This is with the CO2 enrichment. That means with artificial CO2, without artificial CO2. So we can see the ground-based, like that means, or geothermal greenhouse. This is the conventional greenhouse. So we can see the conventional greenhouse, the water consumption is quite high, which could be significantly reduced with the geothermal. Because in that case, we can harvest the waters that's kind of releasing from evapotranspiration. So in terms of the greenhouse emission, so we can see in the greenhouse emission in the summertime, it can significantly reduce, and also in the wintertime, the geothermal greenhouse can significantly reduce the emission. In the wintertime, this difference is very significant because it's mostly relies on the boiler base, and that has a high greenhouse gas emission compared to the geothermal waste, which almost has negligible emission in terms of the energy use, but other operation has some impact in terms of the emission. It's very significantly different. The operational cost wise, you can see in winter for sure you can significantly reduce the operational cost. In the summer, it's slightly higher in terms of the operational cost, especially the geothermal, because as I mentioned, like it's a mechanical system, more technology oriented things, and in the summertime, it's basically the evaporating cooling works very perfectly. The regions like California where outside is dry and hot, so you can very efficiently use the evaporating cooling system for cooling. But you can see the water consumption is quite high. So that's a big challenge for the California. The same trend we can see also for a higher elevation of the CO2 concentration, but we can see this impact we can minimize with the high CO2 concentration, because when you have high CO2 concentration as a kind of closed greenhouse, and that can help to improve the yield. When you have the higher yield, you can normalize that things, and you can reduce the overall operational cost for 1 kg of the production. But one problems we found, like, okay, like if you use the geothermal system like this, you can imagine you continuously pumping the heat to the ground, or continuously kind of extracting the heat from the ground. So that what will be issue, like especially for some regions, like let's say in Houston, where heating cost is very high, where is negligible cost for the cooling. But the other regions, like let's say in Canada, very north, where the heating cost is very high, cooling cost is very negligible. So what will happen? So, and the research found that if you continuously pump the heat inside the ground temperature will increase. Or if you continuously extract the heat from the ground temperature will be decreased. That will create a big problem for the system, because it's a very expensive system you are designing, and for the long runs, after 2 or 3 or 5 years, the system will not work efficiently. So we recommended some kind of hybrid design for the regions like Houston, where the climate is very extreme for for the heating, for the cooling perspective. This is kind of showing the climate in Houston. I will skip, quickly go to the results. So you can see this results is kind of showing the performance in terms of the total cooling, sensible cooling, and the total heating for the geothermal based greenhouse. So we can see one thing is even in the winter time, to some point, they need the cooling for the greenhouse in Houston. And this is showing the key results. So without the hybrid system with the cooling towers, this is with cooling towers, this is without cooling tower. So we can see when you have the cooling towers, for sure you have some energy consumption for the cooling tower spam operation, but you can see the overall power consumption per square meter is less than 20, even peak July, whereas the without cooling towers, the peak power consumption is even close to or more than 26. But more important results is here. You can see that whatever the heat that you have to dump inside the greenhouse, it's basically you can manage most of the heat by the cooling towers, and then the rest of the heat you can manage inside the ground. So if you do that approach, what you can see the benefit. This is the conventional ground source heat pump. You can see the ground temperature is increased, and it could be go for 24 degrees Celsius. And if the increase like every year by years, it could be increased like even up to that level when the ground source heat pump will not work anymore. But if you have a hybrid system with the cooling towers, you can see the ground temperature fluctuation is not that much, 1 to 2 degrees Celsius, but that could be balanced out over the year. And the next slide will give you the overview how the hybrid system is beneficial in terms of the ground temperature control. So you can see even for 10 years of our simulation, this is showing the fluctuation of the exit fluid temperature for the ground heat exchanger, but this black line is indicate the ground temperature. So you can see it could be almost balanced out when you optimally design the ground heat exchangers and also the ground source heat pump, and that can helps to kind of minimize the issue that can bring for the conventional ground source heat pump, and especially for the regions where the heating cost or the cooling cost is a very high and kind of imbalance. So that like there could be a very easy chance to have imbalance in ground temperature, and this ground source heat pump or geothermal based technology will not work anymore. So that's kind of brings me to the end of this presentation. For at least 4 or 5 different technology, how this technology helps to minimize the energy and water, as well as how the integration of this renewable based operation minimize the impact in terms of the environment, like how it can reduce the greenhouse gas emission. So ultimately, it's give you an idea that how we can achieve towards the net zero in terms of the energy efficiency, and also how the different approach for integration of the renewable energy system or renewable energy based operation of the heating, cooling, and the dehumidification system to minimize the carbon emission from this energy intensive indoor food production like greenhouse. This is my current lab groups, like the PhD student, postdoc, and the master student. And this I would like to also acknowledge the different funding agency. Without that support, for sure, this is just it could not be accomplished. I think I'm done. I'd be happy to take the question from the audience.
Well, we've got 3 questions ready, or 4 questions, and I've got 4 or 5 written down anyway. I'll start with one of my colleagues, Raul. He's put the question in: what are the farmers and the industry's perception of incorporating these advances? So, for example, in Spain, is this all still kind of space research to them, and they've not integrated it, or are they accepting of this research and using it?
So it's depend on, like, let's say, like if I go one by one, the quantum dot technology. So I mentioned it's very like you cannot expect the same benefit everywhere. So some commercial greenhouse, like where the low light intensity is an issue, so they're using kind of shifting that light from blue to the red and ensure that the plant growing is doing better, especially the low intensity regions, especially even the cloudy, when the mostly the cloudy, it's more on the diffuse light, right? That's more on the very low intensity for the red. So from that aspect, it is beneficial, and some growers is adopting that things. Even in Canada, is like
Yeah.
commercially greenhouse doing that things. For geothermal, it's some greenhouses are doing operation commercially with the geothermal in Japan and other regions, but it's a very high capital investment. But as I mentioned, like if you can reduce the operational cost significantly, that's I showed from our research, that can help to kind of balance out that high capital investment with the reduced energy, reduced operational cost. For solar technology aspect, some of the technologies still like kind of very early stage, like as I mentioned, the design, the silicon-based solar cell is a transparent. It's we don't know, like maybe next 50, 20 years after that, you can see that practical. But other technology, let's say, as I mentioned, the tracking, the checkerboard design of the PV shade skin, those are kind of very, very commercialist, acceptable, and like people are adopting those technologies.
Okay.
Yeah.
So another one then is its comparisons on cost. So you mentioned that the geothermal, it's big investment, but actually long-term return would be really good because it's reducing your ops cost. The solar tuning, too early to say on cost, and the quantum dot looks like it should be an easy adoption already. I mean, I've no feel for the costs of production of quantum dot. Is it cheap?
Quantum dot, I don't have the actual number for the pricing, but based on my discussion with my industry collaborator, it's expensive, but it's not crazy expensive. Like it's not like something that's unaffordable by the farmer. It's not like some cheap technology. It's quite. They said it's quite within the economical range, and when you have the better production, and then probably they can minimize the impact of that high cost. But I don't have any economic number at this point, at least.
And presumably, is the quantum dot stuff film? It's a film you put across the glass. You're not embedding it in the glass, or are you?
So traditionally, most of the research for the quantum dot for greenhouse application was for the plastic, because that's easy to do and that's more common for low-tech greenhouse.
Yeah.
But in our case, we try to kind of work with the same company to, let's say that if you previously did that things for the plastic, why not for the glass? Because glass is more common for large scale greenhouse production in North America and even in Netherlands and other part of the world. So in that case, like if we can see the same benefit for the glass and it's practical, then I think it will cover the more wider kind of stakeholders than just focusing on the plastic.
So the quantum dot one always interests me because it's an interesting phenomenon that you're downshifting the wavelength, or you're upshifting the wavelength down, reducing the frequency. I can't remember which one. You know what I mean?
It's shifting the wavelength basically.
Yeah. So basically, though, there's an energy deficit in the downshift. So is this just dissipated heat across the system? And is that heat dissipation problematic?
So
if you're
heat
shifting
dissipation from which?
when you're shifting down the wavelength, you're creating a lower energy wavelength. So where does that energy difference go? Is it just dissipated in heat across the film?
Yeah, so that's I showed, like even like if you're shifting that things, there is not that much change in terms of indoor temperature. So that's we found that it's not changing in terms of anything's the indoor temperature. So that's why like we try to show that the BPD and the temperature variation inside the greenhouse.
So the quantum dot one then, is it how broad scale is the downshift? Do you have to have a specific design, which means it downshifts this band of wavelengths to that band, or has it got a broad? Can you have mixed quantum dot through it to shift different ones to that one wavelength? So can you shift UV to blue, for example?
So in this case, like the result that we present, it's mostly we shift the blue and some portion of the UV, very small portion of the UV. You can tune it kind of, my understanding, like from different spectrum to the other spectrum, but technology wise sometimes some spectrum is challenging. depending on the material composition. So shifting from blue to the red, I think my understanding is maybe easier compared to the other shifting. But if you can shift major portion of the UV, that could be beneficial. But thing is, like for UV, most part the UV is reflected by most conventional glass or plastic. So that's a bit challenging even to transmit that things to the glass or the plastic.
Yeah, I mean, it always struck me if the UV is being reflected anyway, but if you're downshifting it, you're actually increasing the usable light load.
Yeah, so in that case, you don't have to only change the quantum dot, you have to change also the glass, because the glass need to be transparent to the UV, right? So, or the plastic.
Unless you're using a film.
Yeah.
But if you use a film, you get around that.
Yeah. So these are all possible things, but sometimes some shifting could be costly in terms of the quantum dot, and some shifting could be.
I mean, it's an interesting question there again about if you're embedding it in the glass, for example, does that impact on the glass's properties? So does it become a bit more fragile, or it's fine?
No, it's just the glass. Whatever the glass, you are just pasting some kind of a layer on top of the glass.
Okay. So given your experience then, where are you going to see things like quantum dot mainly used? In the very high energy arid areas rather than the cooler areas like Northern Europe?
So it's mostly I think I would like to see the benefit will be where the kind of balanced weather condition, especially let's say where the light intensity is low, it's not going to be very beneficial. Like if you think about in California for the summer, but it's going to be beneficial where the winter the light is a big issue.
Yeah. Okay. Let me just check in case there's one's popped up at the bottom here. So I think we'll avoid the geothermal because in terms of time, but certainly for the interesting bit on the EV systems, it was interesting to me. If you're using them in areas where it is hot and arid, often the problems with PV is dust on top of the PV systems. So your efficiency kind of just goes down fast.
Yeah.
Do you see that as a problem?
Yeah, no, that's the big problem for sure. That's why for most of our case, we are focusing on the indoor shade screen, not the glass.
Yeah.
So the shade screen will be inside the greenhouse that can minimize the impact of the dust or others, the environmental impact. So that's why our main focus was initially the inside the greenhouse, as a kind of replacement of the shade screen or the energy curtain. Yeah. But you will lose some energy production if you put inside, but at the same time, you can do the benefit, as you mentioned, the dust one benefit. Another thing is if you put the inside, the planned evapotranspiration will also cool down the flame to some point, and that's kind of dual benefit too.
So I'll give a final question then. So you've talked about 3 key innovations there. Has all of this been thrown into something like a digital twin to map out how these things can work and interplay and and also running a glass house is hugely complex anyway, so it needs a systems control.
So we work on the digital twin on the control aspect. I didn't present today because that was not the focus, but especially for this technology aspect, there could be many application of the machine learning, especially optimize the glass, different spectral tuning. There is a potential to use the optimization problem that could be solved for the technology, to further optimize the glass, those kind of things. For now, the results that I presented, we did the optimization. That's not based on the machine learning. We did based on computational fluid dynamics. That's more on engineering tools that we commonly use for the light-related optimization. Yeah.
Cool. Well, thanks, Shamim. I think we've questioned you enough. I think it's been a hugely informative and data-packed talk. I'm sure it will garner many more hits on the YouTube channel we put it onto. So thanks for your talk today, and I'm sure we will be back in touch soon. So thanks everyone for attending today. Shamim, you can go and enjoy your breakfast now.
Bye.
See you. Bye.